In this video, we are going to be looking at the effusion and diffusion of gases. By the end of this video, you should be able to define and explain effusion and diffusion, and state Graham's law and use it to compute relevant gas properties. The mean free path is the average distance a molecule travels between collisions. As pressure decreases, the mean free path increases. The particles are farther apart, so they're going to be able to travel farther between collisions. Usually, this mean free path is hundreds of times the diameter of the molecule. Diffusion is the process by which molecules disperse in space in response to differences in concentration. The net movement of molecules is going to be toward the region of less concentration because this is where there will be less collisions, a greater mean free path. The equation for rate of diffusion is the amount of gas passing through an area divided by unit of time. And we can use the same equation for the rate of effusion as well. The rate of diffusion is going to depend on the concentration gradient, the amount of surface area for diffusion to take place, the distance gas particles must travel, the molar mass, and the temperature. Effusion is the escape of gas molecules through a tiny hole, such as a pinhole, into a vacuum. Lighter gases are going to pass through small holes more easily. The rate of effusion is directly proportional to 1 over the square root of the molar mass. So if we have two different gases that we're looking at, the rate of effusion of A is to the rate of effusion of B, as the square root of the molar mass of B is to the square root of the molar mass of A. In this question, it says it takes 243 seconds for 4.46 times 10 to the negative fifth moles of xenon to effuse through a tiny hole. Under the same conditions, how long will it take 4.46 times 10 to the fifth moles of neon to effuse? Well, we're going to use the rate of effusion of xenon is to the rate of effusion of neon, as the square root of the molar mass of neon is to the square root of the molar mass of xenon. But in order to do that, we first need to find the rate of effusion of xenon. Well, we have the number of particles, 4.46 times 10 to the negative fifth moles, divided by time. So the amount of gas that passed through divided by the time gives me the rate, which is 1.835 times 10 to the negative 7 moles per second. I can plug that into this equation. Rate of effusion of Xe is to the rate of effusion of neon, as the square root of the molar mass of neon is to the square root of the molar mass of xenon. And I can look the molar masses up in my reference table and plug that in for the rate of effusion of xenon, cross-multiply to get the rate of effusion of neon, and I get 4.679 times 10 to the negative 8 moles per second. Well, then I can just plug that into the same equation I used at the beginning. The rate of effusion of neon is equal to the number of particles divided by time, and it gave me 4.46 times 10 to the negative 5 as the particles, divided by time, cross-multiply, and I get that it will take 95.3 seconds for 4.46 times 10 to the negative 5 moles of neon to effuse.